Hey everybody, welcome back to Physics Screencast. Today what we're going to do is tackle problems that involve changing motion, and you're going to see us use all of our good coping strategies that we've been talking about because as we progress, the lists of information can get longer, and we're going to need to stay organized. So, like a lot of problems, this one's part of a story. It's just mentioning a little bit of info about the McLaren F1, which really is an amazing car. And what they do is they get into the physics problem part down here where they tell us that the car accelerates from 0 to 45 meters per second in a time of 6 seconds. So what I'm going to do is use the list part of my LEPS, and for changing motion problems, what we do is we want to use this many variables. There's going to be 5 of them: velocity 1, velocity 2, time, distance, and acceleration. And what we're going to find is that we need all of these. So from reading the problem, it looks to me like the car starts the problem going that fast, ends the problem going that fast, and all of that change took a time of 6 seconds. The problem is going to ask us to go and figure out acceleration and distance, so it's actually kind of common that we're going to end up with 2 unknowns in the midst of doing this problem. Now, the equation part of LEPS says that we should write down the formulas that we need to know and think about them. And the 2 formulas that you use for changing motion problems say that distance equals average velocity times time, or acceleration equals change in velocity over change in time. And one of the things that I tried to do in working this out on the iPad is to leave enough space to do the basic math that these 2 little pieces of the equations are going to ask me to do. So you know how I like to look down my list and make sure that I've got everything in terms of units that are compatible. So I've got meters, I've got seconds, and that's all I've got. So that's great. But one other thing that's nice about having your information in a list is it gives you a little bit of space to work. So I know that velocity average is v1 plus v2 over 2, and I can add those 2 in my head pretty fast and come up with 45 meters per second over 2, and the list gives me a little bit of room to do some scratch work. So 22.5 meters per second looks to be the average velocity. Then I can go ahead and use this other part of the equation to go ahead and figure out change in velocity. And if you remember, change in velocity is v2 minus v1. So it looks in this problem like change in velocity is 45 meters per second minus nothing, or just 45 meters per second. So that when I get around to doing my 2 equations, I have all the pieces that I need to really fly through this. So when I write down my equation, d equals v average times t, I'm going to just plug in 22.5 meters per second, time of 6 seconds, and I go ahead and calculate that, and I get 135 meters. When we go ahead and turn to the next equation, acceleration equals change in velocity over change in time. We'll just plug in there 45 meters per second over 6 seconds, and that works out to be 7.5 meters per second per second. So it turns out that McLaren is almost as quick as gravity, which is a freaky thing for cars to be. So there you go. That's one problem, and we'll go take a look at one particularly interesting one in just a second. So here you go. Question number 5 on page A-21 of our workbook gives us a chance to look at a really typical but a really challenging kind of physics problem to do. In this problem, what we've noticed is going on is that a driver of a car is cruising down a roadway, and they give us a speed for sure, and they tell us that he sees a Mustang in front of him 40 meters ahead. They tell us that the best the car can do is slow down at a rate of 8.5 meters per second, so they're giving us an acceleration, and they're asking us if we can avoid a crash or not. I always call these a does he crash question or does he hit the moose question, just in honor of this this problem right here. And you'll see this in a lot of different forms as you go through Physics 1. what I'm going to do is use my LEPS and go and make a list of everything that I know for sure, and we'll use that to organize our thinking too. So we've got definitely a velocity 1 of 27 meters per second, and definitely acceleration of minus 8.5 meters per second. And you might wonder why I didn't put in a couple of the other numbers right now. And the fact of the matter is, we don't really know for sure if this driver gets to 0 meters per second, and we don't really know for sure if this driver travels 40 meters. So the big thing that I'm going to stress right now is an important problem-solving tactic that I hope you really listen to and you think about it. My strategy for these is always the same, and that makes them really easy to explain. I think it's the easiest way to explain them. What I'm going to do is assume that this driver definitely stops, and what I'm going to do is find out how far it takes him to stop. And then if he stops in less than 40 meters, I know he's good, and if he stops in more than 40 meters, I know he's not good. So that's the logic behind what I'm going to do. So if you can just do those two things, then the rest of this becomes pretty straightforward. I'm going to do a little bit of my sidebar math like I've gotten in the habit of doing. I have V average equals V1 plus V2 divided by 2. So that's handy because one of these numbers is 0. So I'm going to get that V average is 13.5 meters per second. And I'm going to get delta V as V2 minus V1. So I actually get a negative change in velocity of 27 meters per second for this driver, and that's all fine so far. So we're just going to pause for a second and clear the screen and go ahead and get my equations out. So I said that the equation that really mattered to us was that we were going to have to go and figure out how far this car travels and go from there. But if you paid attention to my list of information that I had, you notice that I didn't actually have time. So this turned out to be a little bit of work for us because we're going to have to think about how we can figure out time. And to me it looks like this equation right here is one that we could help solve and do it in a way that's going to give us the amount of time. So what I'm going to do is cross multiply both sides by delta t and get delta t times A equals delta V. And then what I'll do is divide both sides by A and come up with delta V over A. And then once I do that, I'll swing it over on this left-hand side of the screen, delta T equals minus 27 meters per second over minus 8.5 meters per second, and that is going to give us how long it'll take the driver to stop. So we go ahead and grab the calculator and figure that out, and it comes out that this is going to take 3.18 seconds for the driver to stop all the way. And the thing is, this is a rock solid number as long as we know that we're going to assume that the driver goes ahead and stops. And it's based on an assumption. It's based on the assumption that the driver can stop. But what we can do is now plug in a really straightforward way to our other equation, t equals V average times t, and we figured out that V average was 13.5 meters per second, and we go ahead and multiply that by our 3.18 seconds, and we grab the calculator here and figure it out. And what we find out is that the distance the driver is going to travel is 42.8 meters. So there you go. That's how you do it. Does he crash question or does he hit the moose question? What that shows to me is that the driver was still moving when he reached the 40 meter mark. So unless the moose got out of the way, or I don't know what else happened, unless the driver could swerve, then he was going to hit the moose. I'll leave it to you to figure out how fast you think he was going if he hit that moose. So there you go. See you next time. Have a great day. Bye.